start. All right. Hello from my side again to everyone. It's a great honor to be presenting. Of course, thank you to the alumni members for taking the time to read all of our thesis in order to grant this award. Of course, it's just a cherry on top on this satisfaction that we have for completing the thesis and for completing our degree, but it's a very meaningful win in our back to be recognized in this way for our efforts. And then without much further ado, I would like to get into showing you my thesis. Starting from the greatest question, why does my research matter, or why should you be interested in these results, and what is the imposing question that we are trying to solve? Well, this surprise given the topic title, it comes as a response to the ongoing data crisis. The data load that we store in the world is increasing exponentially pretty much, and with this comes the necessity to store all the data as well as to move it. It's becoming apparent that the limitations regarding its size of the Moore's law, or rather the number of transistors per chip can no longer increase exponentially per year as before. This leads to a plateau in the computational speeds. And on the other hand, the inherent structure, the inherent architecture of today's computational systems, meaning the von Neumann structure, is imposing both an energy efficiency and a speed bottleneck, given that it separates the memory from the processing units. What arises as a promising alternative, which has garnered significant attention in the past years, is this approach of neuromorphic computing. With on the right-hand side here on the slide, I show a single neuron, which is the fundamental processing unit in a neural network, as I'm sure you all know, and it consists of some linear operations on the left and a nonlinear operation on the right side. It resolves some of our issues regarding the computational speed and the efficiency, because it does not separate the memory from the processing unit. And furthermore, if we apply this neuromorphic computing paradigm in the optical domain, it can lead to a further increase, given that some calculations, such as matrix multiplication, is faster in the optical domain. So then it seems that this optical neural network, and it may seem so because they're quite simple to attain, or that this solution has been implemented. It's notoriously difficult. We are targeting, in fact, functions in optics. So then how do optics? And this is a principle with that lasers in themselves are a cavity which consists of two mirrors, and there is an electromagnetic wave oscillating between these two mirrors. A laser is an oscillatory system, but unfortunately it's a very complex one. So I would like to first explain the concept of injection locking on a simpler oscillatory system, or on a set of pendulum clocks. So pendulum clocks are oscillatory system with this oscillating, of course, pendulum. And you can see that these two have pendulums that are oscillating kind of out of phase, or they're mismatched. Each is oscillating with its own frequency. If we imagine that they are mounted on the same wall, meaning that there is some sort of interaction between the two oscillatory systems, this is a very important point. After some time, I illustrated a few minutes of time, their oscillations will actually synchronize. One of them will keep its oscillation frequency and its phase, while the other one will adapt to it. The one that keeps its oscillation is the primary one, and the one that adapts is a secondary one. And then in order to switch back to the world of optics, our oscillatory systems, which will align to each other, are of course going to be lasers. Now I move to my experimental scheme, and of course, in this scheme, I use my two lasers. I show you the entire experimental scheme as I did do an experimental thesis, but of course, I will simplify it to only highlight the very important sections. starting from the master laser section, which will keep its frequency. And the laser that we used for this one oscillates at only one frequency. We call this a monomode laser, and it has only one peak in its optical spectrum. Keep this in mind. Then the next section that's important is the Fabry-Perot laser diode section, which is our secondary laser. This laser has multiple frequencies, or rather it oscillates at multiple frequencies, meaning it has multiple peaks in spectrum. And as I mentioned the spectrum so far a few times, I also wanted to highlight this spectrum analyzer section, or the actual measurement section of my scheme. So if we simplify it, we get this little scheme. And as I said, it's important to look at the spectrum. On the bottom right corner here, I visualize what that laser cavity actually looks like. I mentioned in the optical pendulum example, in the pendulum clock example, that it's very important that we have some interaction between these two systems. And how do we force then an interaction between our two laser systems? Well, we actually insert the signal from the master laser into the cavity of the Fabry-Perot laser diode. What this looks like is that at low powers and at first, we have the two oscillations happening at the same time. However, after some time and after we reach a high enough power of the master laser, the oscillation of the secondary laser actually aligns to the master laser. And what we get is a spectrum that looks like this. And actually, this is exactly where the nonlinear function hides. If we record the power exactly at the frequency of the master laser, what we will see is that the output power of the laser will rise non-linearly with the input power of the master laser. And that's exactly what we get. So I say out comes the nonlinear function. As you see, this is the function of the output compared to the input. And this right here, this graph, is the most important result of my thesis. This is why I decided to include it here. However, I cannot linger here very long because, unfortunately, even this was an oversimplification. What actually happens in the Fabry-Perot laser diode, once a signal is injected into its cavity, is a very complex process. And if we just keep increasing the power of the master laser linearly while we keep the signal continuous, we will actually reach this state on the left-hand side, which is the bistable regime. We have this hysteresis loop. And you see that this is not the shape of the characteristic which we want. We actually want this nonlinear, continuous nonlinear type of shape for the activation function. Instead, what we need to do is send short pulses of the master laser into the cavity of the Fabry-Perot laser diode. I show on the right side the result of a simulation that I did where I sent an linearly increasing train of short input pulses, where we actually managed to achieve this train of output pulses whose amplitude rises non-linearly. And this is the core physical principle of how we achieve the optical non-linearity. Now, given some time distance, from my thesis, I also wanted to give a few comments on what I included and what I excluded. I included some sparse literature overview at first. Given some time, I realized that this literature overview was very sparse, and there are many, many different methods that people have tried to implement an optical activation function. Another question that arises is if it's even necessary to go full optical or to consider all optical computing, or if it's better to stick to an optoelectronic conversion, where after we conduct the linear operations in the optical domain, we switch to the electrical domain to apply the activation function there. So it's a whole bunch of questions, and with this also the quality criteria section expands, where we also need to know if our activation function can match the existing optical neuromorphic hardware and so forth. Another thing that I wanted to add with some time is that this research is still ongoing in my group. They are now considering systems with dual injection or with 3 oscillatory systems or 3 lasers instead of 2, with which they can even improve the characteristics of the nonlinear function. And they are also building entire computational systems, which are all optical, where they use this nonlinear activation function to build a so-called reservoir computer. So there is more to come. And finally, I wanted to invite you to some further reading if you're interested in these results. They are partly published and partly expanded even more in this paper published in APL Photonics last year,